Okay, this problem asks us to make a linear model. Just like what I've done in the other videos, I'm going to copy the data to my clipboard. And then I'm going to go down to the bottom of the screen, click Get More Help, Stat Crunch, and Control V to paste it. And then the buttons I showed in the previous videos were Stat, Regression, Simple Linear Regression. So I'm going through this a little fast, but if it's too fast, um, check out one of my previous videos on making linear models in Stat Crunch. But that's it. Make sure var1 is your x variable. The y variable is always the variable by itself. February equals. So February was my y variable. That's the column var2. So for the intercept, 164.25, that's the number that's always hanging out by itself, and the slope is always the number next to the x variable, so 0.72. Okay, the conditions. A we'll check in just a second. Linearity condition, you can check that by looking at a scatter plot. So let's edit this. Let's get, what can we get from here? A fitted line plot, I think that will show the line plus the scatter. Yeah, that's good. So look, the deviation from the line, if we're right here near x equals 0, we have to go up like 200 units or down 200 units to capture all the dots. But if you go to this part of the x-axis, you have to go up by 1,200 units and 1,200 units below. So sorry, that is the linear condition. I was actually doing the equal spread condition. I jumped a line when I was reading that. The linearity condition is that they make an approximately straight line, and they do. They are going. This red line does model the data well. It's just that the spread is not the same throughout, so the equal spread condition is not satisfied. Randomized condition, that can refer to a few different things, but in the text of the problem, it says it was a random sample, so we'll assume that this is satisfied. Nearly normal condition, what you can do is you can make a QQ plot. So I'm going to edit this, and instead of a fitted line, this time I want a residual plot. So if I hit my arrow over, now that doesn't form a perfectly straight line. There's a lot of bend to it. And that's a judgment call, but when it's got that much bend to it, we'd say that the residuals are not normally distributed. Another thing you could do is you could get the residuals, which is where you would save the residuals. That would become a column in your data set, and then you can run a hypothesis test to see whether they are approximately normally distributed or not. You don't have to go that far. That curve is enough, yeah, where it says that's not normal. So, how much on average will card holders who charge it to earn in February? Okay, so this model is a way of predicting for new values. It's not a super good model because of that those conditions that are violated. But if we're going to use that model to predict February based on x equals 2,000, all you have to do is plug in 2,000 into the equation. So 2,000 is January times 0.72 and plus 164.25. So there's what our model predicts. Okay, and then part C, given 95% confidence interval for the average February when January is 2,000. So we want a regression. I closed it in between the two parts of this video. Go back to your regression model where you can just click that options and then edit, or you could run it again. And then here we're predicting for 2,000. They want a 95% confidence interval. So that's what's going to get us that interval for that prediction. Now you got to choose between these two. There's confidence interval for the mean and then confidence interval for the new. $2,000 is not a number in our data set, but it is within our data set, right? The lowest value is 0, the highest value is above 7,000. So 2,000 is within the range of the values of our data set. So we're going to use this part and not this part. This would be for making a prediction outside the data set. And look, here's an intuitive reason why. This interval is way bigger than this interval is, right? When you're making a prediction outside your data set, you have more uncertainty, so your confidence interval has to be bigger. We're making a prediction within the value of our data set, the values of our data set, so the interval is smaller. There's mathematics behind there for why the interval is smaller, but we don't have to go over that proof in this class. I don't remember it from college either. I don't even know if I did that proof, or figured out where that formula came from myself. Okay, so part D, Given 95% confidence with the average decrease in the charges of cardholders who charged 2,000 in January. Decrease in charges. I think we just take the average, the predicted value, and subtract these two intervals. But this isn't something I've done recently. Let me make sure. I'll pause the video and make sure. No, I think I got it. It's because I haven't read the context of the problem carefully. 2,000. Oops. Cardholders charged 2,000 in January. They were predicting $1,604 in February, right? So what's the difference between those two? So you just need to subtract the February interval, the bounds of the interval in February by 2,000. So 1451.96 subtracted by 2,000. Now they're saying decrease. I wonder if that means we should drop the negative sign. Because a negative decrease is an increase, right? It's a double negative. Let's try without it. Let's keep the negative sign in there, I mean. Subtract the bounds of part C, confidence interval. Give an explanatory value. So that's 2,000 to give an explanatory value. That's what we did. So let's try dropping the negative sign. Because a negative, like I said, a negative decrease is an increase. Oh, yeah, you drop the negative sign, but then I don't have it from least to greatest. Right, so when you drop the negative sign, all of a sudden 228.16 is now the least amount. So here, when you do this, you can just take 2,000 subtracted by the upper bound. That's 228.16. Now look, that's on the right. I wasn't thinking very much because that's now the smallest value, so that shouldn't go on the right, that should go on the left. And then when you do 2,000 subtracted by 1451.96, that's bigger. Just make sure things are least to greatest. I had it greatest to least. In Part E, what reservations would a researcher have about the confidence intervals between Part C and D? We noted in Part B that the normal probability plot of the residuals showed a curve. So the confidence interval may not be valid. This Part B says the data are not linear. That's not true. The data is linear. It does make a roughly straight line. It's just it lacks homoscedasticity. It lacks that spread. I mean, it has a spread on the right side of the data. It doesn't have that spread on the left. Residuals show increasing spread. That's true. Here, you can see that with a plot. If you edit, make a plot of the residuals. You can tell that from, look, there's a small amount of spread here. There's a huge amount of spread over on the right side. So it's not the same amount of spread throughout for the residuals. Data are not independent. No, we can assume they are because they said they randomly sampled them. Okay, I think that's it. Alright, just watch out for my boo-boo there, and hopefully all those steps will help you through this problem.